All right, welcome to another exciting episode of Advanced Level Chemistry. Its main part today is Monday, November the 10th, 2025. And today we need to just figure out how to calculate the energy, wavelength, frequency of electron transitions in the hydrogen atom and actually in all atoms. Okay, so today is going to be a day where we're trying to do as much as possible. On Wednesday, you are going to answer all of the, well, first we're going to do test corrections. Then we're going to answer the questions for that flame test activity we did on Friday. Now look, listen to me carefully, especially gentlemen. The directions say to answer the questions on the back of the sheet that I gave to you. But you did all of the spectrum on the back. So you're going to have to answer the questions on a separate sheet of paper. It's going to be due on Friday, and you'll just staple that to the two sheets together. Okay? So Wednesday is going to be test corrections, answer the questions to that worksheet. Thursday is going to be practicing all the math that we're going to do today. Okay, so I'm going to go through it, but then we're not going to take time to practice it today. Thursday we practice. Friday, then we'll come in and talk about that, and then kind of get into the deep, how we actually think electrons are arranged in today's model of the atom. Okay, Friday is going to be a pretty deep day. All right, we will be definitely having a test Thursday, probably Wednesday of the next week. Okay, and then we're going to have to try and do periodic table in like 2 days before Thanksgiving, and then come back and do bonding the couple of weeks we have before Christmas. Okay. So that's kind of the game plan. All right, so on Thursday, we were talking about the hydrogen atom and how can we, when we looked at this on Friday, we looked at it last week, we looked at it Friday in the lab, and anytime we look at the hydrogen spectrum with diffraction glasses, we see the exact same 4 lines. How can that be? Well, Niels Bohr was able to figure it out. And he said that there are only 7 distinct energy levels. That the electron can only be on one fixed energy level or the next. It cannot be anywhere in between. Now the energy levels, the energy that the electron has on any given energy level is given by this equation. He figured it out. Now how he figured it out, I don't know. He's way smarter than me. Okay? I'm just trusting it. But N is the energy level. So on the first energy level, the electron is going to have negative 2.18 times 10 to the minus 18th joules divided by N squared. N being 1, so it's that much energy. Now let me explain the negative number. Okay? If the electron, and which is, by the way, when you turn the power off, the electron is going to be down here. This is what we call the ground state. It's always going to be in this lowest energy. The nucleus is down here. Okay? If the electron's here, he used negative because if I want to remove this electron completely and make it become an ion, I'm going to have to put in 2.18 times 10 to the minus 18th joules of energy. So the positive is how much energy it takes to get out here to where there's 0 attraction to the nucleus. So they're saying, okay, if this is 0, then this is going to be the negative in terms of potential energy. It's just where's the 0 reference point in terms of energy. Okay? So that's why it's considered negative. That's not a big deal, but that's why it's negative. If you understand that, great. If you don't, no worries. Now, but if I go from this energy level to this energy level, and I divide this by 1, and then I divide this by 4, and since we're negative, this is going to be 4 times bigger, 4 times more energy than this one, right? But if I go from here, dividing by, this is 2 squared. If I go to here, 3 squared is 9. So if I divide by 4, divide by 9, now we're only at 2 1/4 times difference. Then if I divide this by 9 and divide this by 4 squared is 16. Now I'm not even 2 times. Now I'm only 1 point something times difference. Then if I go, this is 4 squared and 5 squared, now I'm at 16 and 25. the difference in energy based upon this math gets less and less. So it's not like I ran out of room. The energy levels get closer and closer and closer to one another. Okay? So that's why they're not evenly spaced. It's just a math thing. So, here's the gist. Here's the important part. How do I know that the electron can only go from this fixed energy level to this fixed energy level to this fixed energy level? If it could go somewhere in between, say to right there, and it could then come down to here, that would be some color other than red. Because every color's got its own energy. That would be green, yellow, orange. But have we ever seen green, yellow, or orange given off in hydrogen? Never. Bohr never saw it. A few years later, when I was studying in high school, I never saw it. Okay? In the 44 years that I've been doing this, every time I turn this on, have kids look, we never, ever, ever see anything other than red, teal, violet, violet. Now, we have machines that can pick up these other ones. There's 21 possible transitions. But we get the exact same 21 every time. These are in the ultraviolet. These are in the infrared. We can't see them, but they're there. The infrared's why it gets hot. That's heat. The electron can only have fixed energies. That's the key. That's the most important. That's what quantum theory means. Quantum means specific amount. The electron can only gain or lose specific amounts of energy. When it goes from one specific energy level to the next, it gains a specific amount and then it loses it. Well, how do we make it go up? There are only two ways to make this electron go from here to a higher energy level. Do we remember what those are? Two ways to make light. How do we do it? Turn on the light, turn electricity, right? Electricity will promote the electrons. How'd the cavemen do it? Fire. Heat and electricity are what caused the electron to go up. But we learned earlier in the year that everything wants to be in the lowest possible energy state. So it's just naturally going to come back down. So the light is produced by electrons being forced up by heat or electricity and then naturally falling back down. And when they fall back down, they give off energy in the form of a photon, a packet of energy. Now, Bohr was able to figure that out. So if we look at, so this doesn't ever exist. But if we look at the transition from the third to the second energy level, we can calculate the energy wavelength and frequency of that. This is what we did on Thursday. Okay? So, does everyone remember delta E from 3 to 2 is going to equal what? How do we calculate that? Did we do it? I think we did it. We never did it? I think we ran out of time in here. Okay? Well, if this is a set energy and this is a fixed energy, how do I find the difference between them? Subtract. So it's going to always be, so you probably want to copy this down, E final minus E initial. I know the equation's given to you, but you might even want to, this is going to be fairly extensive map, so you probably want to maybe get out a separate sheet of paper and just kind of insert this in the notes, okay? But the energy on any energy level is given by this equation. Now this equation is always given, all constants are always given, all the equations, all constants are given, okay? Let's get fun. So it's always going to be final minus initial. So if I'm going from 3 to 2, I'm going to say negative 2.18 times 10 to the minus 18th joules divided by the final, which is going to be 2 squared, minus negative 2.18 times 10 to the minus 18th joules divided by 3 squared. Okay, I'm just plugging in. This is the energy of the electron on any energy level. So when we put all that in, this comes out to negative 3.03 times 10 to the minus 19 joules. This is the energy of one photon. What does that negative sign mean? In terms of energy, what does negative mean? I heard somebody say it louder.
It's like giving it up.
It's giving it up. It's releasing it. It's exothermic. That's why we see it. The photon's being released from the hydrogen. It's going out. So energy's released. Going uphill. So when we're turning the electricity on, one of the transitions, now again, you have more than one hydrogen atom in there, but one electron is going to drop from the third to the second energy level. When it does so, it gives off, boop, a burst of energy, a little packet of energy called a photon. That photon hits our eyeball, and we perceive it as a red light. But if we measured the energy in that packet is 3.03 times 10 to the minus 19th joules. Now, 10 to the minus 19th is a very tiny number. That's a small amount of energy, but we're being bombarded by bazillion of them, and so there's enough of them to where they actually make an image. We can see the red line. The more photons that hit us, the brighter that red line appears. But all the photons of red are going to be that same size. Okay? So our pupils dilate and constrict to limit how many photons come in. When it's a bright light, we squint. The pupils dilate because we're being bombarded by bazillions of photons. Too much, our eyeballs are being overwhelmed with energy. But when it's dark, everything dilates so we can get a maximum number of photons coming in so we can get an image. But this is the energy of one photon. When we calculate this, that's how much energy is in one photon. The brighter the light, the more photons. But if it's red, they're all going to be this size. That's the particle nature of light. But it's going to have a certain wavelength and frequency. Well, I know that E equals h nu. Okay? Now, y'all, we're going to do some high-level algebra here. Okay? How do we isolate nu? That's the frequency. Nu is going to equal what? E over h. Okay? Don't forget how to do basic algebra. That's being sarcastic here. E over h. Even in my AP chemistry class, they keep messing this up and saying h over e. Okay? Y'all, you divide both sides by h to isolate the v, the nu. Okay? So I plug in. This is my energy. Okay? Now, once again, everybody listen. What's the negative sign? Tell me. Energy is released. Do you have a such thing as negative energy?
No.
What's the negative sign? Simply tell me. Energy is released. The direction of the energy flow. So we drop the negative sign. You do not have a negative wavelength or a negative frequency. Frequency and wavelength are always positive. Okay? The negative signs simply tell me the energy is being released. We don't have negative energy, but so drop the negative sign. So we simply say 3.03 times 10 to the minus 19th joules divided by h, which is Planck's constant, 6.626 times 10 to the minus 34th joules. That number is always going to be given to you. That's a constant. Planck's constant. And when you multiply all this out, it's going to end up equaling 4.37 times 10 to the 14th per seconds. And a per second is known as a hertz. Named after Heinrich Hertz, who did the photoelectric effect. That's the frequency that this photon is going to be traveling in. That's the wave characteristic. But frequencies have wavelengths. So C is equal to lambda nu. So what's lambda going to equal? Okay? C over nu, right? Now, anybody remember what C represents? It is a constant. It's the speed of light. Again, that value is always going to be given to you, but it happens to be 2.998 times 10 to the 8th meters per second divided by my wave, C over nu, sorry. Okay? Over my frequency, what I just found, 4.37 times 10 to the 14th per seconds. Okay, sorry, now notice I put lambda and lambda. Yeah, hopefully you guys did it right. Didn't follow mine. Yes, just followed my error right over the cliff right there. Okay, I put lambda, it's supposed to be C over nu. Lambda is equal to C divided by nu. Okay, so when you divide all that out, it comes out to 6.56 times 10 to the minus 7th meters. Okay, now I'm assuming you all know how to do scientific notation on your calculator. We've been talking about it all year long. You need to be able to just put these numbers in. I'm not taking the time for you guys to put it all in your calculator. But wavelength is normally in nanometers. Now, we go back 10 weeks, 13 weeks maybe. I don't know how long it's been since August. How many nanometers in a meter? Anybody? How many nanometers in a meter?
6.
One more.
7.
No.
6.
What the next up? It goes in factors of 3. Okay, it's 10 to the 9th. That was one of the ones you're supposed to always know. So this turns out then, when you multiply, here's math again. Hey, by the way, you take algebra, you learn all this math so you can apply it to a real subject. Okay? Math is just a tool that science has created in order to be able to solve our problems. But when you multiply exponents, what do we do with them? Don't listen to him, listen to Anderson. Okay? What did you say, Anderson? You just add them. When you multiply exponents, you add them. So minus 7 plus 9 is equal to plus 2. So it's going to be 6.56 times 10 to the 2 nanometers, which is equal to 656 nanometers. So what, Mr. Hobbs? Well, if you come here and you look on this chart and you see this red line right here, and you have the wavelengths right underneath it, you see that this wavelength that right here is right at 656 nanometers. Bohr is able to explain exactly how hydrogen can give a red line every time. Does it ever give green? Does it ever give yellow? No. It only gives the red, the teal, the purple, and the purple. Because the electron cannot just go and gain any amounts. It can't stop in between energy levels. The energy levels are fixed. It can only go from one. It's like climbing up a ladder. You have to go from one rung to the next. You can't stop in between. The electron can't stop anywhere in between here. It can only gain and lose fixed amounts. Quantum means specific amount. You get a quantity of apples. You're going to get a fixed amount of apples. Same Latin root word, quantum. So just real fast, just right now, if an electron does 4 to 2, what's its energy, wavelength, and frequency going to be on the same sheet of paper right here? You just now do this exact same thing for 4 to 2 in your notes. What's the energy, wavelength, and frequency of an electron transition from the 4th to the 2nd energy level? Hit pause, please. Okay, so once we get to this, plug it in, you should get this. Again, what's the negative sign? Tell me. That's the light we're seeing. Okay, we should be seeing that. That should be the teal color light. The photon, one photon has that much energy in it. So now I want to find, from there, I want to find the frequency. Well, I know that frequency is equal to E over H. So I just plug this in, but I take the negative sign off. 4.86 times 10 to the minus 19th joules divided by 6.626 times 10 to the minus 34th joules times seconds. Again, that's Planck's constant, that's an H. That's always given, it's always that number. That's why it's called a constant. And so this number comes out to equal what? Anyone? No one has this number yet? You guys are just quitting, you're not trying.
Times 10 to the 14.
7.33, anybody get that? Times 10 to the 14th, and that's per seconds, which is 7.33 times 10 to the 14th hertz. Now you can leave it at per seconds, that's a 4. So what do I do with that number then? If I want wavelength, it's going to equal C over frequency. C is always given as 2.998 times 10 to the 8th meters per second, divided by the frequency I just calculated, 7.33 times 10 to the 14th per seconds. Seconds cancel, joules here it cancel. This comes out to equal
4.09 times 10 to the negative 7.
Are we getting all these same numbers? I'm seeing some head shaking. Are we getting some different numbers?
I got a different first number.
Okay.
The very first number.
What did you get?
I got 4.09 times 10 to the negative 19.
4.09?
I got 4.86 as my last.
Okay, 4.09. Okay, so what, I know, so hey, all we gotta do is change answers. 4.09, again, I was trying to ask if everybody agreed, and everybody's shaking their head, yes, they agreed. Okay, so what do we get? What do we get here?
6.17.
Say that one more time.
6.17.
6.17 times 10 to the 14th. And then this comes out to 4.86. Okay? Now, that's meters. How do I go to nanometers?
Times 10 to the 9th.
Times 10 to the 9th, which simply means I add 9. The number doesn't change, so it's going to be 486 nanometers. Now, once again, I come here and I look. Now, it doesn't look teal on here, but the teal line that we see, if you match it up, this line matches up exactly to 486 nanometers. Again, Bohr was able to figure out exactly how hydrogen is giving just 4 lines. The whole key is that the energy levels are fixed. You go from one fixed energy level to another. Okay? Now, this really isn't super complicated math. They're big numbers, they're scientific notation, but it's simple algebra. Yes, sir.
So on the test, would you just tell us to go from 1,
Yeah.
like 3 to 2? Or
3 to 2, 5 to 1, 6 to 3. And then you just have, but the equations are all given, the constants are all given. Okay?
What does H like to stand for?
H is called Planck's constant. He found that when he found E equals H nu, H is a constant, and it's always 6.626 times 10 to the minus 34th. That anytime you have things that are proportional and you have to change it to an equation, there's always going to be a constant. You learn it is y equals mx. M or y equals k times x. K is your constant, and whenever y and x are proportional, in order to make it an equation, you have to have a constant. Wavelength and frequency are proportional. Energy and frequency are proportional. So you got to have a constant in there to make it an equation. For E equals h nu, the constant is h, and he named it after himself. Max Planck named it Planck's constant, and it came out to equal that number. The speed of light is the constant for wavelength and frequency, and that's always given as that. Okay? So whenever two things are proportional to make an equation, you gotta have a constant. Alright, so that's just, we could do this for every single 21 different transitions here. Some are in the ultraviolet, some are in the infrared. We see 4 in the visible light spectrum. One of these is barely in the UV. Now what if it was helium? If it's helium, how many protons does helium have? 2. So if I'm looking at, helium's got 2 electrons down here on the first energy level, okay? But it's got 2 protons. Is that going to be holding those electrons more tightly or less tightly if it's got 2 protons versus 1? More tightly, because it's the positive to negative attraction that's holding the electron in. Positive to negative. So if I have 2 protons, it's going to have a different attraction to my electrons. So when an electron in helium goes 3 to 2, it's going to be still fixed energy to fixed energy, but it's going to be a different value because you got 2 protons versus 1. So it's going to be a different color. It's not going to be that same red line. I go to lithium, it's got 3 protons. So now there's a different attraction to my electrons because there's 3 pluses versus 1. Same basic equation, but we have 3 protons, so that means my transition is going to be different. So every element has a different number of protons. So every element has a different, when it goes 3 to 2, it's going to be a different color. And so we get different transitions, so every element's got a unique number of protons, so every element has a unique set of lines. They have a unique set of energy levels. Okay? That's huge. So right now in this light, you got a kind of a pink light here and a kind of a bluish tint light here. What's the difference, you think? Why do these look different? Okay? What do you think's different on the inside? Different elements. They got different gases. Different gases give slightly different colors. But the way that these are all producing light is we turn the electricity on, and it's shooting electricity through the gas, and the electrons are going up. It's a fancy one of these. Okay? It's a vacuum on the inside. If you've ever broken a fluorescent light bulb, they kind of make a cool sound because they don't explode, they implode because the pressure is less on the inside. So when they break, everything pushes in instead of out. And so there's a gas at low pressure, the electricity goes through it, electrons go up, and when they come back down, they're giving off light. And they have a mixture, so we give off all the white light. But they still have different hues based upon which gases are. Just tidbit, the ones that are slightly pink, they've never been replaced. They're the originals to this room. I've been in this room since the school was built. Okay? And so the white ones, the brighter ones, are the ones that are the new bulbs. But that's pretty good that they lasted 25 years. Okay? All right. So that's hydrogen. And that's nice. But you know what? It only worked for hydrogen. We kind of explain it. But that was all turn of the century, in the early 1900s that they figured out all this. World War I came along, kind of slowed things down as far as research. And then after World War I, a French radio operator named Louis de Broglie started messing around with radios and thinking, he said, you know, Einstein said that light has a dual nature. What if particles have a wave nature? What if matter actually in motion travels in a wave nature? So if you look in the bottom of that page on your notes, you see an equation for what he called matter waves. That any object in motion that you have, what is it? What's the equation? Lambda, it's equal to mass over m over hv? H over mv. Okay, h is Planck's constant, m is the mass, and v is the velocity. That's not a nu, that's a v. That's velocity. Which means that if I hit my 100-mile-an-hour serve down the tee, that serve, even though it looks like it's going in a straight line, it actually has a wavelength to it. It's got a wave characteristic to it. But if you plug in the mass of a tennis ball, the speed of my tennis ball, and Planck's constant, 10 to the minus 34th, the wavelength is very, very, very tiny, immeasurable. So the wave nature of a large particle, the wave nature, even though a car driving down 65 feels like you're going in a wave motion because the road's so bad, okay? The wavelength of macromolecules, things that we can see, is immeasurable. But turns out, if you go and put the mass of an electron going at the speed of an electron, you get a wavelength that's about the diameter of an atom. Ooh, so maybe the electron has wave nature to it. So a guy named Erwin Schrödinger decided, hey, I can treat the electron like a wave, and I can describe the motions of the electron like a wave rather than like a particle. So while having a romantic tryst with one of his mistresses, because back in the early 1900s, the scientific nerds were kind of a, they were ladies' men. Einstein was a ladies' man, Schrödinger was a ladies' man, so he was having a romantic tryst with one of his mistresses, and in between romantic interludes, he actually was inspired and came up with what's known as Schrödinger's equations. He came up with the current model, and I don't recommend that as your motivation, by the way, I'm just telling you history, okay? So he treated the electron like a wave, okay? Grab this in. Walk to that wall. Put your back to that wall. So I'm going to teach you. Keep going all the way. All right. So I'm going to teach you some wave theory. Okay? And we know about crests and troughs already. So if I send a wave down, you can see that one wave bounces back and forth. It goes back and forth. Now, if I send a series of waves, they're going to begin interacting with one another as it goes here. The wave going this way is interacting with the wave coming back. There's two types of what we call interference patterns, constructive and destructive. If a crest meets another crest, a crest going this way towards J and a crest coming back towards me, the two crests meet, one's going to crawl over the top of the other one, it's going to be double high. If a trough meets a trough, it'll go low, it'll be double low. That's constructive interference. If a crest meets a trough, a crest going this way meets a trough coming back, they'll cancel each other out. It's called destructive interference. Okay? That's wave characteristics, constructive, destructive interference patterns. Okay? But if I can get things, yes, sir.
Does a whip work like that?
I mean, you're just doing it, but you're not, it's not, since a whip isn't held at the other end, it's not sending anything back. But I mean, it's definitely going to be, and it makes the sound because you're breaking the sound barrier. Okay, it's why it actually makes the noise. Okay, but that's something different. But if I get the energy going just right, well, get the energy just right, there we go. You just hold your hand still. Okay? Can you see now, this is what we call a standing wave pattern. Just hold your hand still. There you go. So, okay, Reed, come here. You got it. Okay? Just take over after me. Okay, just keep going. There we go. So what we have right here is constructive interference. Crest is meeting crest, and trough is meeting trough, and it's double high. But what we have here is getting weaker and weaker. What we're having here, there we go, is what we call a nodal region where we're having destructive interference. We're having the crest is meeting a trough, destructive interference. But notice that we have a whole number, two crests, and one node. There's a certain wavelength that only this standing wave pattern can form. So now, thank you very much, good job, stay there, okay? If I change the energy, change the wavelength and frequency, now I can have two nodes. But notice that I have three crests, three envelopes, okay? But notice again, it's got to be a whole number. There's only a certain wavelength that this can form in. If I change the energy again, okay? Now we have three nodes, 4 envelopes. But once again, there's only a certain wavelength that it can form at. If I don't, you can do it. Let's go, one more. Okay? Okay? I can only go for a little bit. Now, if I don't get the energy right, we get chaos. There's only certain wavelengths and frequencies that this standing wave pattern can form. Okay, good job, Jeff. Schrodinger was able to derive this exact same equation, but treating the electron like a wave instead of a particle. Now, electron's obviously a particle. It's a particle traveling in a wave motion, a standing wave pattern. Okay? But he still has to have fixed energy levels. There's only certain distances from the nucleus that the standing wave pattern can form. So we have these nodal regions in between where there are no electrons. There's only certain distances, certain energies the electron can be to form a standing wave pattern. Now it got complicated because in Schrodinger's equations, you end up having not only just energy levels, but we're going to have some sublevels. And he's going to have 4 variables that are all related to one another in his equations. And on Friday, we're going to look at that. Now, I don't know if you've ever heard of Schrodinger's cat experiment. This is a very theoretical. It was not done, so you cat lovers, don't freak out. But Schrodinger said that the electron is both a wave and a particle at the same time. Just kind of like we're saying light is a wave and a particle at the same time. Now, an electron is very much has a mass. We can measure its mass. We know what it is, okay? But he said it's a wave and a particle, but we can only measure one thing at a time. So it's like if you put a cat in a box, like just a box, but you can't see into the box. And in the box, there's a radioactive, there's a vial of poison that's connected to a radioactive switch. So there's a radioactive particle that's got a 50-50 chance of decaying. If it decays, it activates the switch, breaks the vial, poison's released, the cat dies. But there's a 50-50 chance that the radioactive element does not decay, therefore the switch is not activated, poison stays in the vial, the cat lives. So unless you open the box, as long as you don't open the box, the cat is both alive and dead at the same time. It's not until you open the box and look at it are you forcing the cat into either an alive or a dead state. That's what he says about the electron. The electron is both a wave and a particle at the same time. However, when we observe it, we force it into one state or the other. So you can observe a photon's mass, its particle nature, or you can observe its wave nature. You can't observe them both at the same time. The more you know of one, the less you know of the other. Now, there is a crazy, if you want to get your mind blown, there is a crazy, go to YouTube and look up what's called the double slit experiment. You shoot electrons through a wall that has got 2 little slits in it. Wave nature, listen, the wave nature makes interference patterns, which means you give a shadow, a light spot, a shadow, a light spot, a shadow, a light spot. It's interference. It's constructive and destructive interference. The electron acting like a wave. If you shoot it and don't look at it, it gives you interference patterns. But if you observe the electron with machines going through the double slits, if you observe it, it goes straight through like BBs would go straight through and does not give an interference pattern. It acts totally like a particle. So somehow, some way, the electron knows if you're looking at it or not. And it actually changes its characteristic, whether it's being observed or not being observed. It acts, if you look at it, it acts like a particle. If you don't look at it, it looks like a wave. Acts like a wave. Look up double slit experiment. If I had time, it blows your mind. It's crazy. Quantum mechanics do not follow any normal rules. Okay, so have a great day tomorrow. Get your work done on Wednesday and Thursday, and I'll see you on Friday. Go Jags.